We're going to continue our discussion in solving first-order differential equations, where we're going to use it to solve simple circuits. In this case, we're going to solve a parallel RL circuit. So we're going to start off with a current source. We'll call I sub S in parallel with a resistor R and inductor L. So here we have a current I sub R through the resistor and a current I sub L through the inductor going in the direction as shown, and we'll label the polarities as a result of selecting that current direction to be as follows. So here, using KCL, the sum of the incoming currents we'll call at node A is equal to the sum of the outgoing currents. So our incoming current is denoted as IS, and our outgoing currents is denoted as IR plus IL. Now, using our element circuit relationships in terms of voltages and currents, we know that the voltage across the resistor using Ohm's law is IR times R, and the voltage across the inductor is L d IL dt. But we know that elements that are connected in parallel, in which case the R and L are connected in parallel, have the same voltage. That is, VR is equal to VL. Using this relationship, then, we can equate this equation for VR and VL. So here on the right side, left side, we have I sub R times R equals L d IL dt. Now here we can solve for IR, which is equal to L over R d IL dt. So substituting in the above relationship here, we can, this equation right here, we can say that IS is equal to LR d IL dt plus IL. And what we have here is a first order differential equation. Now we want to put it in standard form, so we'll solve for d IL dt plus R over L IL equals RL IS. Okay, so once we have that relationship, we just took this equation here and rearrange it, use algebra to get this first order differential equation in standard form. So, finding the integration factor, as we did in the previous two examples, we have E integral R over L dt, which is just E to the R over L t. Now, using